I will discuss a very special type of motion in 2 dimension. It's called circular motion. So what it looks like is that suppose you have an object which moves around a fixed point in a coordinate system. Let's put my coordinate system y and x. These are the axes. So what you see, this circle is the path of this object, this particular object, and it revolves around this origin of that particular chosen coordinate system. So it's always revolving around this fixed point O at a constant rate. I mean, the speed is constant. Okay, so we're going to define this motion of object as uniform circular motion. What is uniform about this motion is that the object speed is not changing, okay, and it's always going back to the same point at an equal interval of times, okay. So suppose at a particular instant of time the object is here and it moves, it circulates in the counterclockwise direction. So in fact, there are two directions for the circulation. It either goes in the counterclockwise direction or goes in the clockwise direction. This is just a convention that we take the direction in the counterclockwise direction. This is the counterclockwise direction as positive, and the clockwise direction as the negative. Okay, this is just a convention. And let's just freeze the time at a particular instant and draw the position vector measured from this origin or the center for the circle, the path, as r. Okay, the position vector for this object. Let's name this as r vector. Okay, so at that instant of time, this position vector makes the angle, let's say theta, with the x-axis. And we know that just again in a convention that if you're working on a polar coordinates, we measure the angle just from starting from the x-axis, and we take the positive angles to be in the counterclockwise direction. So at a particular instant of time, let's theta being the angle that the position vector of the object, as you see as a point, the theta being the angle with the r, the position vector of the object, and the x-axis. Okay, so of course, as the object rotates at a constant rate, at a constant speed, this angle will increase at a constant rate, right? And this angle is usually measured in units of radian, but I mean it's not unit, but the scale of radian. So we can say that, for example, let's make a numerical give a numerical example that if theta is 30 degrees in 1 second, I mean if let's say at time t is equal to 0 the object starts right from this point, which is on the x-axis, and it starts its a constant speed motion, so that it takes, let's say, 30 degrees or pi over 6 degrees in terms of radian, 30 degrees in terms of degrees in 1 second, then the particle will go another 30 degrees in this time t is equal to 2 seconds, another 30 degrees in time t is equal to 3 seconds. So it goes like this. So that means theta, the angle, is going to be proportional to time, right? So theta is just proportional to time. All right, just like if you think about an object going at a constant speed or constant velocity along the x-axis, right? This, let's v being the constant velocity, what we usually write as x is equal to v times t plus some initial position. So you see, if you take the initial position to be 0, this distance is going to be just some constant multiplied by t. Just like this angle will grow linearly with time. So why not we write theta to be some constant times time t plus some initial value for theta at time t is equal to 0. And we can take this theta 0 to be 0, in fact. Okay, at time t is equal to 0, if you start the motion of the object at time t is equal to 0, if you start on the x-axis, so it's going to be naturally theta is going to be 0. Okay, so this is just we figured out that the angle of this position vector of the object can be expressed as a function of time, just like in this equation, and omega being the constant. It's a constant value over here, and we can easily figure out what this omega unit for this omega is. That it should be, since there is no unit for angle, it must be 1/2, right? The unit for omega is going to be just 1/2. Okay, so in fact this omega is nothing but angular velocity. It is called the angular velocity. It is angular velocity because it's about how the rate of change of the angle is changing, how it measures the rate of change of the angle, right? Omega. So it's called angular velocity. All right, so in that case, well, let's start our motion, as I said, at time t is equal to 0 on the x-axis. So omega is going to say theta is going to omega times t. So what next? You may want to express the coordinates of this object at any time. So let's say choose this time being right over here in unit vector notation. So in unit vector notation, what you do is just project this position vector onto x-axis. But since the position vector, length of the position vector will never change. Why? Because it is at a uniform circular motion. Its path is always a circle of a fixed radius, right? So that means its projection onto the x-axis is going to be just length of this vector, which is, let's say, r. Let's put the length to be r, okay, of the vector. It is going to be r times cosine theta, right? But since our unit vector along the x direction is I, we must put r of I over here. And plus, its projection onto the y-axis is going to be r times sine theta j. So the first thing is just we expressed the position vector of the object that rotates around this fixed position in space, doing this uniform circular motion. The position vector can be expressed like this, and since this position changes over time, let's put theta as a function of time, so that r vector is going to be a function of time. R times cosine omega t I plus r times sine omega t j. These omega t's are just the angles for the sine and cosine. Okay, so far so good. And the other thing is that let's talk about the velocity vector of this object. Okay, since you have a complete information of its position, why can't we express its velocity vector? Because we know that velocity vector as a function of time is nothing but just the time derivative of the position vector. This is the definition of the velocity vector. Okay, so if you know the complete description of this vector as a function of time, then you're done. You can just express the velocity. And the other thing is that for 2 dimensions, as I explained this in my previous videos, if you know the path of the object, if you know the path, okay, path is just, is this trajectory in 2-dimensional space, the velocity vector is going to be always a tangent vector at the point that the particle passes from it. So at this point, for example, the velocity vector of this object is going to be just a tangent line, a tangent vector. Right at this point, it's going to be tangent vector. You can easily write this is going to be velocity vector, because we know this from the we analyzed the paths and the trajectories in our previous videos, that if this is the trajectory of the object on space, in 2-dimensional space, at any point you can draw its velocity vector to be, if it goes from here to here, from this point to this point, then the velocity vector at any point, let's choose this point to be this specific point, is going to be just a tangent vector at that point. For example, over here, the velocity vector, instantaneous velocity vector, is going to be tangent over here. At this point, for example, the velocity vector is going to be tangent to the path over here, and so on and so on. So by this token, just the velocity vector at any point is tangent to the circle. And the other thing is that since if you draw a tangent line at any point on the circle, this line is always going to be perpendicular to the position vector. Okay, tangent you draw at any point on the circle, it's going to be always perpendicular to the line that connects that point to the center of the circle, and which is nothing but the position vector. Alright, we can check this. In fact, once we just find the position vector out of this, the velocity vector out of the position vector, we can see that these 2 vectors are going to be just perpendicular to each other. So let's take this derivative. If you take the derivative of this first component, we always take this unit vectors to be constants, and this is constant. The only thing that depends on time is that cosine. It's cosine omega t. And if you take the time derivative of cosine, it is nothing but minus sine. But you have to take also the derivative of the argument over here. Omega t gives you omega when you take the time derivative. So it is just minus r times omega sine omega t I, which is the unit vector. Okay, so this is the time derivative of this first x component, okay, of the position vector. So similarly, if you take the time derivative over here, it's going to be r times omega cosine omega t j. Okay, so this is the position vector, okay, components given in the unit vectors of i's and j's, x and y direction. The I is the unit vector in the, let's say, show it here, in the x direction, and j is just the unit vector in the positive y direction. Okay, so you can check that from these components, the position vector and the velocity vector are just perpendicular to each other. Okay, and by geometry we know this. Also by component wise, you can check this. You can decompose just this vector, v vector, into x and y coordinates. So you can see that these 2 vectors, in fact, they are perpendicular to each other. Okay, all right, so are we done? In fact, the next question that you might ask yourself is that, well, can we express, first of all, the velocity, the speed of this uniform circular motion. Okay, can you find the speed of the uniform circular motion from this expression that you just got the velocity in terms of the i's and j's, or unit vectors. So to find the magnitude of the velocity vector, well, after all, let's call this is the speed v as the magnitude of the velocity vector, and we're trying to get that this information that, since we are talking about a uniform speed, this v should be a constant value, right? Let's figure this out. And can we have this v, the magnitude of the velocity vector, to be independent of time? Although you see over here this velocity vector v, in fact, let's put also this dependence over here of time. Although we have time dependence over here, can we have the magnitude of this velocity vector to be time independent? Because we just say that the speed must be constant. It should be just independent of time, because it's always going with the same speed. So let's check this. I mean, we're just going to take the square of this first component minus r omega sine omega t squared plus the square of the second component r omega cosine omega t squared, and take the square root. Okay, so if you look at this expression of this sum of two squares, what you will get is just r square omega square, and also you will get r square omega square from the second term, so we can take the r square omega square parentheses, and from this first term we will get sine square omega t, plus from the second term we will get cosine square omega t. But if you look at this trigonometric expression, that sine square plus cosine square of the same arguments, it is nothing but 1, because sine square of some angle plus cosine square of some same argument is nothing but, we know from trigonometry, it is a constant of 1. So what you get is, inside this square root, okay, you only will get r square omega square, and this r square omega square term just runs out of the square root as r times omega. R being the radius of the circle that the object just circulates, and omega being the angular speed or angular velocity. Let's say angular speed because it's not vector over here. So you see, v, the speed in the uniform circular motion, is nothing but equal to some multiplication of two constants, right? R is constant and omega is another constant, and v is just independent of time, right? So that's, you see, if want to see that whether speed depends on time or not, obviously we shouldn't have a time dependence, because we're talking about uniform circular motion. That means a constant speed circular motion, all right? Constant being the constant of time. Okay, so that's good. And you also see there's a relation between the linear speed of the object, or the path speed, or the trajectory speed of the object, is somewhat related to the angular speed through this constant, where constant being the radius of this circular motion. Once you know the angular speed, and once you know the radius of the circle, you can just calculate the speed of the object, and that's a good thing. Just from the knowledge of these two things, the angular speed, the rate of change of this angle, and if also you know the radius of the circle, you can just calculate the speed of the object. All right, the linear speed of the object, or this arc speed, the trajectory speed of the object. So the next thing that we should ask ourselves is that, well, we have a constant speed, and the speed of the velocity vector does not change over time. But does that mean that the object has no acceleration? Well, it's not true, because the acceleration is defined, the acceleration vector is defined to be time derivative of the velocity vector, right? And obviously, the velocity vector depends on time through this equation. So when you take this derivative, you will see that the acceleration is not zero, right? Let's calculate this. Okay, the first thing that you should do is let's take the derivative of the first velocity component over here as function of time, and this will give you, if you, the sine omega t is the only term that depends on time. These are constants, including the unit vector, but derivative of sine omega t is nothing but omega times cosine omega t, and 1 omega over here, 1 more omega over here makes minus r omega squared cosine omega t I to be the first component of the acceleration vector, or the x component of the acceleration vector. Next is, if you take again the time derivative of this second component, the y component, what you will get is minus r times omega squared sine omega t j. Okay, so obviously what you see over here is that, you know, first of all, the acceleration is not zero, it's a well-defined vector. And the other thing is that, let's make an observation. Let's ask, if this is the acceleration, it's non-zero, what is the direction of the acceleration of this object? Okay, the next thing is that, can we find its direction? Later we will also calculate its magnitude. Okay, so if you observe that these r omega squared terms common for both components of the acceleration vector, but what I will do is that I will just pick up omega square minus omega square term as the common thing, and I will take the parentheses r cosine omega t I plus r sine omega t j, and it will be obvious now that why I did this is that when you observe this vector r cosine omega t I plus r sine omega t j, it is nothing but the position vector itself. Okay, this is nothing but the position vector. So some negative quantity, which is over here just the minus of square of this angular velocity, multiplied by the position vector. So the acceleration vector is nothing but some constant multiplied by position vector, but this is negative. So this is immediately tells you about the direction of the acceleration vector. It's just inverse of the direction of the position vector, because we have a minus quantity in front of it. So the acceleration vector will be just toward the center at any point of the motion. If the object comes over here, the position vector is going to be this one, and the acceleration vector is going to be just inverse of the position vector at any point. So you see, the acceleration vector is nothing but, first thing is that the acceleration is not zero, although the speed is constant. The velocity vector is not constant, it's always changing its direction. Okay, that means there is a change, some measurable change in the velocity vector. Whenever you have a measurable change in the velocity vector, then you have a non-zero acceleration. So let's talk about its magnitude. If you take the magnitude of the acceleration vector, it's going to be just omega square times r, right? Because magnitude of the position vector is nothing but the radius of the circle, and the circle is just being the trajectory of the circulating object. All right. So, well, if you know its trajectory speed or linear speed, okay, path speed, if we want to express the acceleration vector, let's put small a over here, because we know that there is a relation between omega and v, the linear speed. Omega is nothing but v over r. If you put the v over r over here, okay, if you put v over r square, so v square over r square, because omega is v over r, and you multiply this by r, you will get that the acceleration, magnitude of the acceleration, is nothing but, in terms of its speed, v square divided by the radius. Okay, so this is the proof of the acceleration, magnitude of the acceleration vector to be v square over r for the uniform circular motion. Okay, so far let's summarize all the results we got over here. That theta is just omega times t, but to be most general, we should add this initial angle, theta 0, because the object may start with a non-zero angle at any point. Then in that case we should put this initial angle over here, and v is just omega times r, and a is v square over r, or you may put a is equal to omega square times r. So next question is, and the last one, that let's start at one particular point, and let's suppose that you know the radius and you know the speed of the object that circulates doing this uniform circular motion. Let's talk about this time that for this object to make its complete one revolution. Start from this point and make one complete revolution, come to the same point again, and this is a special time which we put as a capital time. It's called the period of the motion. This is the period of the motion. The period in a uniform circular means the time it takes to make the object one complete revolution. Okay, well, can we express this period or time, specific time, for the object in uniform circular motion in terms of the radius and the speed? If you know the radius and the speed, can we write this period in terms of the radius and the speed? Well, of course you can. It will be just, the amount of the path, or the length of the path that the object makes, divided by its speed, right? So the length of the path is nothing but the circumference of this special circle, which has the radius r, which is 2 pi times r, and divide this by the speed. So this is the period of the object. Okay, and if you want to express the period in terms of omega, where omega is the angular speed, omega is just v over r, let's put this, instead of v over here, 2 pi r divided by omega times r, you get just as expression of the period 2 pi divided by omega. As long as you know the angular speed of this object, you can easily express the period in terms of the angular speed as the inverse of the angular speed multiplied by 2 pi. So in that case, you see, the period only depends on one variable, one physical quantity, which is nothing but the angular speed. You may express the period in terms of the radius and the linear arc velocity or arc speed of the object, but this equation, this relation, it looks like simpler than this one because it only depends on the angular velocity. As long as you know the angular speed, you can just know what the period is. But the period is inverse of some other quantity which we call frequency, and the frequency is defined to be, if you just look at your watch, run your clock only 1 second, and just count the number of turns that the object does in 1 second. For example, if the object makes 2 revolutions in 1 second, we call that its frequency is just 2 seconds. Sorry, 2 hertz. Because in 1 second it makes 2 revolutions. And in that case, the frequency is just 2 hertz. And 2 hertz is just the unit for the frequency, and hertz is nothing but 1/second. It is equivalent to 1/second. Okay, so if it makes 3 revolutions in 1 second, that means the frequency is 3 hertz, and so on and so on. Sometimes this omega that we defined as the angular speed, sometimes it is known as the angular frequency. Omega is known as sometimes the angular speed, or angular frequency. And this f is called the linear frequency. It is just the inverse of the period, and from this you can have a relation between the linear frequency and the angular frequency to be f being just to be omega divided by 2 pi, or omega to be just 2 pi, the linear frequency. Okay, so these are all the information you have for an object which moves around a fixed point at a path of a circle which has a radius r, and this is all you got for that specific type of motion, which is we call uniform circular motion. You know what its position vector at any time, you know what its angular speed, you know what its linear speed, you know how to express its acceleration in terms of linear speed and the radius, also in terms of its angular speed and the radius, and you know what its period, and you know what its frequency, and you know what its angular frequency. They're all, here, they're all, we just derived from only the position vector. And it's very incredible that by just writing what the position vector is, we derived all the things like velocity vector, the acceleration vector, the magnitudes of them, etc.